Before the 1970s, tank armor relied primarily on mass and hardened steel alloys to defeat kinetic energy penetrators. The introduction of Chobham armor fundamentally changed this paradigm by prioritizing material hardness and energy dissipation over sheer thickness. This composite structure, developed at the UK's Chobham Tank Research Centre, was first publicly deployed on the American M1 Abrams and the British Challenger 1 main battle tanks. Its core innovation lies in using extremely hard, brittle ceramic tiles encased within a metal matrix. When a long rod penetrator strikes the ceramic layer, the localized high pressure causes the ceramic to fracture into a fine powder. This process consumes significant kinetic energy and, crucially, causes the incoming projectile itself to shatter, yaw, or erode rapidly, preventing deep penetration into the hull. This mechanism provides superior protection against high-velocity, armor-piercing, fin-stabilized discarding sabot rounds compared to equivalent-weight steel armor. Chobham armor is not a single material, but a classified composite laminate structure. The basic configuration involves a layer of high-hardness ceramic tiles bonded to a ductile backing plate, typically steel or aluminum alloy, and often confined by a thin metallic faceplate. The ceramic component is the primary defense layer, usually composed of high-purity aluminum oxide, known as alumina, or silicon carbide, depending on the required threat level and weight constraints. Silicon carbide offers superior hardness and lower density compared to alumina, making it preferred for weight-sensitive applications. The tiles are typically hexagonal or square and are precisely fitted to minimize gaps, which represent ballistic weak points. The confinement provided by the surrounding matrix is essential. It maintains the structural integrity of the ceramic under intact, maximizing the time the ceramic remains effective during the penetration event.
Ceramic Matrix Composites, or CMCs, are defined by a ceramic reinforcement embedded within a ceramic matrix, but in armor applications like Chobham, the term often refers to the ceramic metal composite structure. The key ceramic materials used include boron carbide, silicon carbide, and alumina. Boron carbide, with a Mohs hardness of 9.3, offers exceptional performance against tungsten carbide and depleted uranium penetrators, but is significantly more expensive and challenging to manufacture into large tiles. Silicon carbide provides an excellent balance of cost, density, and hardness, making it a common choice for modern modular armor packages. The manufacturing process involves hot pressing or sintering ceramic powders at high temperatures and pressures to achieve near-theoretical density, minimizing porosity, which drastically reduces ballistic performance. The quality control of these tiles, particularly ensuring uniform grain size and minimal internal defects, is critical for consistent ballistic resistance. The effectiveness of the ceramic layer relies on inducing catastrophic failure in the kinetic energy penetrator. Upon impact, the high shock impedance mismatch between the steel penetrator and the ceramic tile generates intense compressive stress waves. These waves travel faster in the ceramic than in the metallic penetrator. The ceramic material, due to its high compressive strength but low tensile strength, resists initial penetration. As the penetrator attempts to push through, the ceramic layer generates lateral tensile stresses within the penetrator itself. This lateral stress causes the brittle tungsten or depleted uranium rod to fracture into multiple smaller fragments. The resulting debris cloud has a much larger surface area and lower momentum per fragment, drastically reducing its ability to penetrate the subsequent backing layers. This process is often described as the ceramic eating the penetrator from the sides.
Beyond fracturing the projectile, the ceramic layer absorbs energy through two primary mechanisms: comminution and friction. Comminution is the process of the ceramic tile breaking down into fine powder, consuming energy through the creation of new surface area. This process is highly efficient in dissipating the kinetic energy of the impact. Simultaneously, the interaction between the fractured ceramic fragments and the eroding penetrator generates significant frictional heat, further slowing the projectile. The stress wave propagation within the composite structure is also crucial. The impact generates a complex pattern of reflected and refracted waves at the interfaces between the ceramic, adhesive layer, and backing plate. Proper design ensures that reflected tensile waves do not prematurely cause spallation on the interface of the backing plate, which would endanger the crew. The thickness ratio between the ceramic tile and the backing plate is optimized to maximize energy transfer and minimize structural failure. The ductile backing plate serves multiple essential functions after the ceramic layer has performed its primary role. First, it acts as a catcher plate, stopping the residual fragments of the projectile and the ceramic debris cloud. Second, it absorbs the remaining momentum through plastic deformation. Materials like high-strength aluminum alloys or specialized rolled homogeneous armor steel are used for this layer. Third, the backing plate provides the necessary confinement pressure to the ceramic tiles. This confinement is crucial because ceramics perform best under compression. Without adequate lateral support, the ceramic would fail instantly upon impact, offering minimal resistance. The entire composite module is often encapsulated in a lightweight casing, ensuring the tiles remain tightly packed and pre-stressed, maximizing their ballistic efficiency even before impact. A separate internal spall liner, typically made of aramid fiber or ultra-high molecular weight polyethylene, catches secondary fragments and minimizes crew injury.
The primary advantage of Chobham-type armor is its superior ballistic efficiency, measured as protection per unit weight, often termed the mass efficiency factor. Against kinetic energy threats, composite ceramic armor can achieve protection levels equivalent to much thicker and heavier steel armor packages. This weight saving is critical for maintaining vehicle mobility, reducing fuel consumption, and allowing for the integration of heavier weapon systems or electronic countermeasures. Furthermore, the ceramic composite structure is highly effective against shaped charge warheads, such as those found in rocket-propelled grenades. The ceramic layer disrupts the formation and penetration of the metallic jet by introducing lateral forces and causing the jet material to flow unevenly, a mechanism known as jet breakup. This dual threat capability against both kinetic and chemical energy projectiles makes CMCs indispensable for modern armored fighting vehicles. Despite its protective benefits, ceramic composite armor presents significant logistical and cost challenges. Unlike homogeneous steel armor, ceramic tiles suffer catastrophic localized failure upon a single high-energy impact. Once a tile is struck, its ballistic performance is severely degraded, requiring replacement of the entire module. This necessitates modular armor design, where damaged sections can be quickly swapped out in the field, increasing complexity and maintenance costs. The manufacturing process for high-quality ballistic ceramics is inherently expensive, involving specialized high-temperature sintering and precise machining. Furthermore, the export and technology transfer of advanced ceramic armor compositions are tightly controlled under international agreements, such as the Wassenaar Arrangement, due to their strategic military importance. This legal restriction limits the availability and drives up the acquisition cost for allied nations.
Modern iterations of Chobham armor, often referred to generically as Dorchester or specialized packages like Mexas, utilize advanced modular designs. These systems incorporate layers of different materials, including high-strength steel, titanium alloys, non-metallic composites, and sometimes reactive elements. Modular armor allows commanders to tailor protection levels based on the mission profile and anticipated threats, optimizing the trade-off between protection and mobility. For instance, add-on armor panels containing CMCs can be bolted onto the base hull structure when facing high-threat environments. Some advanced systems integrate explosive reactive armor elements or non-energetic reactive armor into the composite stack to enhance protection against tandem charge warheads and improve multi-hit capability by disrupting subsequent impacts. The trend is towards lighter, thinner ceramic tiles combined with advanced fiber-reinforced polymer backing plates to maximize weight savings while maintaining ballistic integrity. Future developments in ceramic armor focus on improving multi-hit capability and reducing weight through nanotechnology. Research is concentrated on transparent ceramic materials, such as aluminum oxynitride, or ALON, which could replace traditional glass laminates in vision blocks and periscopes, while offering comparable ballistic protection to opaque ceramics. Another area involves developing nanocrystalline ceramics, where extremely small grain sizes enhance fracture toughness and potentially mitigate the single-hit failure mode characteristic of current macrograin ceramics. Furthermore, advanced modeling techniques, including finite element analysis, are optimizing the geometry and arrangement of ceramic tiles, moving beyond simple square or hexagonal shapes to interlocking structures that better distribute impact energy and minimize stress concentration points. Legal frameworks governing the proliferation of these advanced materials will likely tighten as their effectiveness increases, impacting global defense markets.